Alright guys, we're going to jump into vodcast 10.3. We're going to talk about solubility graphs. This is going to be a little bit different than the lessons we've been doing lately, because while there are some definitions and stuff that you can see there in your notes, it's not really about definitions and it's not really about math. It's about looking at a graph and being able to interpret it. And the good thing here is if you can interpret a graph here, that's going to serve you well in other areas like the ACT. So first off, we're going to talk about solubility, and solubility basically just means how well does a particular thing dissolve in a particular solvent. Now, most of the time our solvent is water, and if you remember in the last couple of sections we talked about this general rule of thumb that almost always is in quotes, okay, and that is that like dissolves like. Okay, and just to review real quick, what does that mean? That means that polar things dissolves polar, okay, and nonpolar dissolves nonpolar. And remember that when we talk about polar, we can include ionic in that as well. So what does that mean? That means that typically something like water is going to dissolve something like salt. Okay, salt is ionic, water is polar, and so those two things are going to dissolve each other. To sort of talk about something that it wouldn't work quite that same way, water and something like, say, carbon tetrachloride, which is a nonpolar molecule, those two things are not going to dissolve very well because water is polar, carbon tetrachloride is nonpolar. Okay, so that's solubility basically, that something, how well something dissolves in a particular solvent. So what are the factors that affect how quickly this happens? Okay, because really, like dissolves like is all we're going to get into what solubility actually is. It is more complicated than that, but we're not going to delve too deeply into it. So instead what we're going to talk about and focus on are how much stuff we can dissolve and then how quickly we can get it dissolved. And that quickly is right here. Okay, so when you see rate of dissolution, think about quickness, or how quickly something dissolves. Okay, so what sorts of things are going to affect that rate of dissolution? Well, first off, we have a pretty simple one. So like, you started to make your Kool-Aid and you put some sugar in it and you put the Kool-Aid packet in it, and then you just let it sit there, right? No, I mean, of course, the first thing that you're typically going to do to help things dissolve a little bit more quickly is you're going to do some stirring, or we might say some agitation, okay, or depending on the type of container that we're in, perhaps some shaking. Okay, so we're going to stir things up, we're going to shake them up in some way that we're going to agitate them. And what that does is it allows the solvent particles to get around the solute particles so that they can attack them in that way that we talked about dissolution in 10.1. Okay, so that's our first way that we can affect the rate of dissolution. Second way that we can affect the rate of dissolution, okay, has to do with something called particle size. Okay, and this one, again, relatively easy to understand. Particle size, or sometimes it's called surface area, and it works like this. So we've got big crystals here and smaller crystals here, much more finely granulated, kind of big, chunky crystals right here. Which of these do you think is going to dissolve faster? Okay, the way it works is that the more area that the solvent can get to attack, the better, or the more quickly it's going to dissolve it. So what that essentially means is that the smaller the particles, the more finely ground they are, the easier they are to dissolve. Big chunky crystals don't dissolve very quickly, but little finely granulated things are going to dissolve pretty quickly, and that's why sometimes like to make things to make drinks sweet that are already cold, because it's obviously pretty hard to make them to add sugar once it's already cold. Like you guys know when you get that glass of unsweet tea and it was supposed to be sweetened, so you try to put some sugar in it and it just never, I mean, you stir it up and the sugar all sits at the bottom because it's cold. Sometimes you can get super fine sugar, which is almost like powdered sugar, and since it's much smaller particles, it will dissolve a lot more quickly. This is also why we talk about using a mortar and pestle in the lab. So a lot of times in the lab, I'll get these big giant crystals like this. Then I'll take the mortar and pestle and basically sort of grind them up until I get much smaller particles there. Okay, so that's point number 2 that's going to affect the rate of dissolution. The last thing that's going to affect the rate of dissolution is something also that makes pretty good sense, and that is heating the solvent. Now, this one is a little different than the other ones in that it's not always true, and we'll see that here in a second. But in general, that's true. So when I was just talking about the idea of, like, you get unsweet tea and it's got ice cubes in it, and you put the sugar in it, and the sugar never dissolves. Well, that's because when are you supposed to add the sugar to tea? You're supposed to add it when it's still hot, because when it's still hot, the sugar will dissolve pretty easily, right? And it's still the same amount can eventually dissolve, but the speed of it dissolving is going to be a whole lot quicker in that hotter water than in much colder water with the ice cubes in it. Okay, so heating the solvent up generally is our third thing that's going to help us to affect the rate of dissolution or speed it along. So just to sum up real quick, what are the three things that help us out with our rate of dissolution? First one is stirring or agitation of some kind. The second one is the particle size, make things smaller. And the third one is to heat up the solvent. So if you were asked a question on a test that said, what could you do to help this solution dissolve? It's not going to dissolve. You can list any of those three things, and they would help it out. Okay, so this is what we call a solubility graph. We're going to use the solubility graph to explain a bunch of different things, and we can tell a whole lot of information from a relatively simple graph like this. You've got a graph like this in your notes. Okay, so make sure that you're looking at that. The first thing that we want to talk about are two definitions, and these hopefully are on your notes. But the two definitions that we want to talk about first are two words called unsaturated and saturated. Now, these may not be in the order that they're in your notes. I don't actually recall what order I had them in, but once I explain them, you should be able to tell pretty easily what they each are. So here's the deal. Let's look at, for the moment, let's just look at one line. Let's look at this green line here for potassium chloride. What this green line says, shows us is that if you look on the left-hand side here, okay, on the y-axis, it says solubility in grams per 100 grams of water, okay? So what does that mean? That means that if I have a container that has 100 grams of water in it, okay, that I could add a certain amount of my solute in there and it will dissolve properly, okay? Now, the amount that will exactly dissolve and no more will dissolve, that is the saturated amount. So a solution is said to be saturated when it has the maximum amount of solute dissolved in it. So what the chart tells us is what that maximum amount of solute is, okay? So if I was at 30 degrees, okay, which is down here, and I went up on my chart till I got to the green bar there, where KCl is, it's right there, okay? And so then I would read across, and that's at about, I don't know, 37.5 grams, okay, something like that. Obviously, it's a graph, so I'm making a little estimation. That means that I could put 37.5 grams of KCl in 100 grams of water at that temperature, okay, at 30 degrees Celsius. Now, what you can see from the graph is that that solubility, okay, or that saturation point, it's called a couple of things. It's said to be saturated at that point. It's also said to be its solubility at that given point. You can see that that changes depending on the temperature. So, like if we went down to 20 degrees, okay, and we're still talking about KCl, and I read across there, I'm at something like 33 or 32 grams. And then if we went down to 0 degrees around freezing, it'd be down around 27. You go up to 100 degrees where the water's almost boiling, and we can put in about 55 grams. So a solution is said to be saturated basically when it lies on the line for that particular chemical. Okay, and as you can imagine, there's only 6 chemicals here. There are millions and millions of chemicals. They each have their own solubility, so they would each have their own individual solubility graph. Okay, so what saturation means is that it lies directly on the solubility graph, okay, directly on that line. So if I was talking about, say, potassium nitrate at 50 degrees, I go down here 50 degrees, and I go straight up, and I hit potassium nitrate, and that means that potassium nitrate, I can put 80 grams in per 100 grams of water at 50 degrees. Okay, at 40 degrees, I can only put 60 grams of that potassium nitrate in. At 30 degrees, I can put a little over 40, okay, and so on and so forth. So it varies pretty strongly with temperature. Now, you'll see a couple of things. Most of them go up and some of them go up pretty sharply as we heat things up. If you look at something like salt, its solubility does increase as temperature goes up, but not by much. I mean, it starts out at 35 at 0, and then it's about 40 at about 100, so it doesn't increase much. Potassium nitrate shoots up pretty quickly. Sodium nitrate shoots up pretty well. Potassium chloride's up, so is the potassium chlorate. But if you look down here at the cesium sulfate, what you actually see there is that its solubility actually decreases as it goes down. And that's why we said that that last thing about the heating the solvent up helps. That's usually true, okay, but not always. So all of that sort of explains what saturated is. Now, let's go back to the idea of unsaturated. What does unsaturated mean? Unsaturated means that you are anywhere below the maximum amount. So like if I was at 40 degrees, okay, so 40 degrees right here, and I was worried about KCl, and I only put 30 grams in there, okay, that's much less than the maximum. The maximum is 40 grams, and if I only put 30 grams in, okay, that is what we call an unsaturated solution. Unsaturated means that it is below the maximum amount, below the solubility point, or below the where it's saturated, then it's unsaturated. In other words, I can put more in there. And the easiest way to sort of think about that is like a sponge or a paper towel or something like that. If you dunk it in the water, it's completely full of water, right? I mean, it's saturated. You could wring it out and get all the water out, but it can't hold any more water. But maybe if you just had like a couple of drops spilled on the counter and you put the paper towel in it, and just like one half or one corner of the paper towel got wet, that paper towel is then unsaturated. I would have to use, it would take more water to saturate that whole paper towel. Okay, and the same thing would be true here. I've got 30 grams in it. It would take 10 more grams to completely saturate that solution of potassium chloride. Okay, so that's two of our terms. Let's talk real quick about one more of our terms, and that is something really sort of weird called supersaturated. Now, here's the problem with supersaturated. The prefix super means above or more, and so what this really means is above saturated. And you're like, but didn't you say that saturated was the maximum amount? And it is, okay? So how do you get more than the maximum amount? Well, here's the way it works, okay? So let's say that I have a solution of sodium nitrate at 20 degrees, okay? So we got sodium nitrate at, that's a terrible at sign, at 20 degrees Celsius, okay? So, and let's say that it's saturated at that point, okay? So I'm going to just make a little note here. It's saturated. So let's read off and see how much that is. At 20 degrees, it takes about 90 grams to fully saturate it. Okay, so that's 90 grams worth, right? And then, and here's the kicker, let's say that we then cool the solution down to freezing. Okay, so we go down to 0 degrees Celsius, which is about right here. So it's about 72 grams at 0 degrees. Okay, here's the thing. I put 90 grams in it. I was at 20 degrees. I dissolved everything I could. I had 90 grams in it, and then I cooled it down. That difference, okay, and the difference, of course, if we subtracted it, is 18 grams. That difference stays in the solution, okay? It's still dissolved. And so even though my maximum amount is 72 at 0 degrees, I have an extra 18 grams, okay? So I am super saturated. I am above saturation. Now, the way supersaturation works is that if you agitate it or do something to disturb it, then all of that extra stuff, in our case, the 18 grams, the supersaturated part, is going to come out of solution. The classic example of that is something called rock candy. The way that they make rock candy is that they supersaturate a solution with sugar. Okay, so they heat it up, okay, to near boiling. They dissolve as much sugar as they can at that temperature, and then they cool it down. Okay, and so that solution becomes supersaturated. And then what they do is they put the little rod or the stick or the string or whatever in for the rock candy. And as soon as that happens, it crystallizes, and all of the excess stuff, all of the supersaturated stuff, the difference, okay, between the original saturation and the new saturation point, all of that stuff crystallizes out. So like, let's say that instead of sodium nitrate, these values were for sugar, I would get 18 grams of sugar to crystallize here. because it was supersaturated. Okay? So that's how we use a solubility graph. And what I'm going to do is I'm going to walk you through a bunch of problems. If you turn your note sheet over, we're going to walk through a few problems about how we apply this and what we actually do and what kinds of questions we can answer from a solubility chart. So, question number 1. At what temperature can 50 degrees of potassium chloride dissolve in 100 grams of water? Okay, so here's the way we would find that out. I'm at 50 grams, right? Now, it says 100 grams of water. What does that mean? That's what my graph is defined in terms of. It doesn't have to be. It could have been defined in terms of 1,000 grams of water. This particular graph, though, is 100 grams. Okay, so 50 grams, and then I'm going to draw myself a line until I get to KCl. Boom, right there. Okay, where's that at? Now, you can kind of tell where it's at because there's nice graph lines on here, but if we drew that line straight down to the temperature, what do we get? 80 degrees Celsius. So at 80 degrees, I can dissolve exactly 50 grams. We would say that that was a saturated solution. So question 2, what is the solubility? Let me move this up just in case you can't quite read that. Shrink this down just a tad for us. Let's get rid of that extra stuff. Okay. What is the solubility of potassium nitrate at 30 degrees? So how do we find that? We go to 30 degrees. Okay. I go up until I hit the line for potassium nitrate. In our case, potassium nitrate is that yellow line or yellow orangish line. So it hits right there. And for solubility, that basically means how much dissolves. So once I draw that line there, I draw it over to the solubility line. And it's somewhere around 45 grams per 100 grams of water. Okay, that's the solubility. So basically, almost all this graph stuff kind of just goes in, can you plot stuff? Can you find where you are on the graph, okay, and be able to interpret the graph? So let's answer a couple of more questions real quick, and then we'll be done with this section. So which compound has the highest solubility at 20 degrees? And that one's real easy. It's just like you're looking at the graph. I'm at 20 degrees. Which line is the highest? Okay, well, pretty obviously that's sodium nitrate. If you were asked to tell the second highest, okay, that is a little bit more interesting because we're at 20 degrees. We go up. So it's not potassium nitrate, it's not potassium chloride, it's actually sodium chloride at that point. Okay, because that line right there, that is the second highest. Okay, so sodium nitrate and then sodium chloride would be next. Okay, question 4 is a pretty interesting one, and actually there's a little typo in here. That should be cesium with 3 sulfates. If you wanted to dissolve more cesium sulfate at 10 degrees Celsius, should you heat it up? So we go to 10 degrees Celsius, okay, and we're right there. We can dissolve about 10 grams. So what happens if we heat it up? The solubility actually goes down. Okay, so that's kind of a big fat no. Okay, what should you do actually if you wanted to dissolve more? I should cool it down. Okay, if I cool it down, the solubility actually increases. And again, that's not really the norm, but it definitely is something that happens occasionally. And then our last question here, a saturated solution of potassium chloride at 80 degrees. Okay, so 80 degrees, it's saturated. I'll come up there. That means I've got about 50 grams, right? And then it says it's cooled to 40 degrees. Okay, so it's cooled to 40 degrees. So at 80 degrees Celsius, how many grams do I have? I'm just going to make myself a little note. That's 50 grams. And at 40 degrees Celsius, I can have 40 grams. So it says what mass of crystals could that form? That basically says it's supersaturated, and it's supersaturated by how much, okay? And that's pretty simple. Then you just do a quick little bit of math there. So what's 50 minus 40 is 10 grams. So I would get 10 grams of potassium chloride crystals in that case. All right, we're going to work through a bunch of this kind of stuff in class, guys. Don't be afraid of this. Graphs are entirely doable. In fact, this is a lot easier than doing the math stuff, in a lot of cases easier than even doing memorization. You just got to look at a graph and be able to read it.